Hello and welcome. In this problem, a wedge with a given half angle is given, which is standing on the way of a supersonic flow. To negotiate the wedge, an oblique shock is created, shown here. And this is called theta, the angle the oblique shock makes with the axis of symmetry. So the flow is turned around. M1 becomes M2, is still supersonic. The flow is turned around, and M2 is of course parallel to the the wedge to make sure the boundary condition is satisfied. To solve the problem, we recognize that across the shock behaves just like a normal shock. The oblique shock in this direction, tangential direction, in the normal direction, is just nothing but a normal shock with the normal Mach number m1 sine theta being the strength of the shock. So given the delta, our strategy would be first to calculate theta, then find the mn equal m1, which is 2 m1 sine theta, and then use the shock table to find the given ratios. So let's go, and we already are in the gas dynamics tables. So the delta theta table is right here. We expand the table, and I already put Mach number 2. If you calculate, and delta equals 8, so theta is found, as you can see, is 37.2 degrees. Notice that if you put the pointer over theta, there are possibly two solutions. The second solution is shown here. If you go take a look at this location, you will find there are two solutions. So oops, I already erased that. Anyway, so if you go put your pointer over theta, you can see that in addition to 37.2 degrees, there is a strong shock angle of 85 degrees. We'll keep it in mind because the second part of the problem says at what angle, what delta the shock disappears. In other words, when these two angles become equal, you can show that you cannot sustain an oblique shock after that angle. So now that we know theta, we can go find the Mach number m1n. We can do it with a calculator, but I did it with an equation here just to show you how to use the IO panel. So m1n is 2 is my Mach number, and sine of theta must be in radians. That's why I have to multiply that by pi divided by 180. Note that one of the things that we don't have the ability is to pick up the variable from the tables. IO panel understands all the variables from the state panel, but not from the table. So anyway, so m1n is found to be 1.1859. So we'll copy that 1.1859 and go back here in the normal shock table. We are going to paste it and Control V. Yep, I got it. Calculate. So that produces the exit Mach number, the normal exit Mach number, but all the ratios that was wanted in this problem: temperature ratio, total pressure ratio, etc. So now that all these are found, to find for the last problem, as I just mentioned, all we have to do is to keep changing delta. Suppose we say, okay, delta is not 8 degrees, it's higher. Let's say it's 10 degrees. So that will produce a higher theta, and we put the pointer over theta to see what is the value of the strong shock. Again, it's still 30, pretty different. So you keep increasing until I think the answer is, I have already got it written here, 22.6 degrees. So if delta is 22.6 degrees, then theta is 60 degrees, and if you put the pointer over 60, you'll see that the two angles are pretty close, 60.8 and 68.3. So basically slightly higher than that would be the delta for which the curve looks like this. In other words, this is the delta theta plot. So essentially we are looking for this point at what delta we get the strong this is the strong solution and this is the weak solution, they become equal here. So that's what is wanted. So when delta is so high, what happens is that there is no oblique shock is possible and a bow shock is created in front of the wedge.